So we were discussing the linear discriminant analysis, and we saw that under the assumption that the distributions for the different populations, could be two more populations, are normal, then under the assumption that they have the same variance covariance matrix, the linear discriminant function delta sub k of x is just a linear combination of the x's. That's why it's called a linear discriminant function. Okay, and we would assign the observation with the x, with the p variables given by x here. We would assign that observation to the group or to the category that gives a maximum for this decision boundary. Okay, and we also said that in practice we never know the prior probabilities. We estimate them by the proportions of each of the classes in our sample. We estimate the sample means the usual way, and we estimate the sample variance covariance matrix as a pooled matrix, because we're assuming that all variance covariance matrices are the same. Okay, now we require, to be able to estimate the discriminant function, we require that the sample size minus k, which is the number of classes, is greater than 0. Okay, so we have to have enough observations. So that happens, that's normally the case. That should be an issue. This is a picture that shows how these linear boundaries look like. These are 3 samples generated from bivariate normal distributions with different means. Here you can see the means in these crosses here that were generated, that were used to generate these samples, and the same variance covariance matrix. You can see that it's the same variance covariance matrix because of the form of these ellipses. Okay, this would be like 95% ellipses, so they look exactly the same because they have the same variance covariance matrix. The linear discriminant function is just going to be in this case, it's going to be lines that are going to separate the groups. We have 2 dimensions, so it will be lines. If we were working in 3 dimensions with p equal 3, then we would have hyperplanes separating the groups. If we have 4 dimensions, hyperplanes, and so on. Okay, so graphically, it's easier to see it with 2 dimensions. More than 2, we could visualize an hyperplane, but it's not that clear. So the important thing here to notice is that essentially we have boundary that are linear for each pair of classes. Okay, this is separating these 2 classes, and this would extend here. Okay, that's why this line is like in this left chart extends all the way, and this extends also all the way here, and also this one extends all the way here. Those are the linear discriminant functions. Okay, now for simplicity, let's move to the case where we only have 2 groups, and so the linear discriminant function is going to be the linear combination of the p variables that maximizes the distance between both groups. Okay, we're maximizing the distance between both groups. We can write these linear combinations as transformations of this type. Okay, it's some constants multiplying each of the p variables, and we have 2 groups only. These linear combinations would look like this. I have 1 linear combination to separate based on transform my variables from 1 population, and the other linear combination transform my variables from the other population. Essentially, the linear discriminant function that we saw earlier, the delta sub k, is going to be given by the vector of a's, of constants. These are the parameters of the model that maximize the distance between the transformed means. Essentially, what linear discriminant analysis is doing is rotating the axis so that I can separate the means of the groups as much as possible, and I have as small a variance as possible within each of the groups. That is essentially what the function is doing. When we estimate this thing, this is, we can estimate this thing by maximum likelihood, but this will be equivalent to finding the coefficients of these linear combinations of my x's that maximizes the difference between the means, separates the means as much as possible, divided by the this will be the variance, right? In the case of these two dimensions. This will be, I can write this thing down in matrix form. This is when we maximize this function, it turns out that A is the inverse of the pooled variance covariance matrix times the difference between the original means. Okay, x bar 1 minus x bar 2. So these are transformed variables with this linear combination, and the coefficients are given by the inverse of the matrix of the variance covariance matrix, which is the estimated by pooling both sample variance covariance matrices, times the difference between the original means. If we had J groups, then the pooled estimate of the variance covariance matrix is going to be an average of these pooled variance covariance of each of the variance covariance matrices for each of the J groups. Okay, here I have J groups, so I'm taking just the average of all the variance covariance matrices for each one of the groups, and that will be my estimate of the common variance covariance matrix, the pooled estimate of the variance covariance matrix. Now, it is clear that since I'm maximizing this thing, any vector A would work, but what matters is not the actual vector, but the direction that that vector is defining. Okay, the direction is what's important. So again, here we require that the sample sizes for both groups -2 greater than P. Okay, that's a requirement to be able to estimate these functions. This is what's happening. Imagine we have two variables x and y, and they belong to the green and the black population. Okay, they belong to the green and the black population. What the linear discriminant function is doing is finding a rotation of the axis so that a straight line would separate both groups as much as possible. If you look here at this data and then look at the transform data, when I made this rotation, then I have a better separation between the blacks and the black population and the green population. Okay, and that's what the linear discriminant function is doing. Is trying to maximize. For example, here this would be around here. You would find z bar 1, and around here you would find z bar 2. So you're transforming so that you separate the transformed means as much as possible. That is essentially what's happening. Okay. Now, this is what's called Fisher's discriminant analysis. Fisher derived this discriminant function without assuming normality. Okay, so he did not assume normality. So in that sense, Fisher's discriminant function is non-parametric. However, he assumes that the variance covariance matrices of both populations, or the 3 populations or 4 populations, are exactly the same. That's the only assumption he makes. Now, in the case of normal distributions, Fisher's discriminant function is going to be the same as the linear discriminant function that we just saw earlier. Exactly the same when we have normality. Now, if we don't have normality, they may be different, but they will separate the groups roughly in very similar ways. Okay, because all we're doing is rotating the space to separate to get a better separation between the groups, the black group and the green group here. And that's Fisher's discriminant analysis. Okay. Now the assumptions is, of course, the grouping target must have a limited number of different categories. Okay, I have to have a 2 categories, 3 categories, 4, and so on. They usually will be small number of categories. Okay. The cases must be independent. Okay, each observation must be independent. That's another assumption that we need to make. The predictors must have normal distributions. That is, this assumption is for LDA. For LDA, not for Fisher discriminant analysis, okay? Which I'll denote by FDA. So in Fisher discriminant analysis, we don't require normal distributions. We just require same variance covariance matrix. Both Fisher and linear discriminant analysis assume that the variables, the predictors, are continuous. Okay, both assume that the variables that predict that are our predictors, the factors, are continuous. The groups have the same variance covariance metrics. That's an assumption of both LDA and, so this applies to both LDA and Fisher discriminant analysis. Every observation has to belong to one and only one group. Okay, so the groups that I have are exhaustive, and all observations can only belong to one of the groups. Now, these methods, linear discriminant analysis and Fisher discriminant analysis, work better when the target variable, our objective variable, is actually categorical. Okay, because for example, we can let's suppose that I'm trying to see if I can predict the age range of some individual based on some other characteristics. So I can artificially generate a variable that says it's going to be 1 if the person is between 0 and 15 years old, and it's going to be 2 if it's between 16 years old and 25, and so on. So I'm creating categories based on a continuous variable. If I don't have the actual values for the age, then it's better to use age as a response and then use a regression model to predict. Okay, not to categorize in groups. Okay, that's what that refers to. If belonging to a particular group is based on the values of a continuous variable, for example, the IQ or weight or height and so on, it's like the example that I gave you. If it's age, the response, then we're better off using regression models instead of classification models. Regression is also to predict. I want to predict the response based on the values of my independent variables or my predictors. Okay. In classification, the objective is, again, a new observation comes, we don't know what class it belongs to, and we need to predict which class that observation belongs to based on the factors or the predictors that comes with that observation. A new patient comes in, and based on his clinical indicators, and want to predict if the patient is having a heart attack or not. Okay, or an admissions committee in a university wants to classify applicants as very likely to succeed or not, depending on their grades in different in high school, for example. Okay, and same thing happens in psychology and psychiatry. Supplies a battery of tests that assign a patient to different types of mental illnesses. For example, based on some characteristics, the patient and answers to certain questionnaires and all that, will that first patient be schizophrenic or not? Okay. Identify an author based on the frequency of certain words or phrases. That this thing here will go in the area of text analysis. Okay, and we use the same models, that we use for other predictive, for all prediction situations. But the same also are especially useful here, in particular, when we are trying to analyze text and predict if a certain text comes from some author or some other author. What has shown to work very well are neural networks and something that are called recurrent neural networks. Okay. In engineering, classification is called pattern recognition. Okay, in engineering they call it pattern recognition, but it's essentially the same. Okay, this is the Fisher's discriminant function, and what we're doing again is we're rotating our axis so that when we start working in the new axis, notice here these are my original axes. Okay, my y and y2. Now, with my transformation, what I'm doing is I'm doing a rotation so that when I project these populations, these samples into the new axis, which is my new axis, Z, when I do that, I get a good separation between the two groups. And then my rescission rule will be to assign, once a new observation comes in, I compute Z. So let's suppose that I have new observations X null. Okay, so I compute Z of X null. Okay, so I have replaced X null here, and I find out if that value is closer to X bar 1 or X bar 2. And according to which one of those two is closest to, I would assign it to group 1 or to group 2. Okay, so it's just a rotation. That's Fisher's discriminant function. Okay. So in that sense, there's some similarities with principal component analysis, because principal component analysis is doing the same thing, is rotating the space. Okay. The difference, and the very important difference here, is that here we're rotating the space considering a response. We're rotating the space so that we can separate better the groups that we have. In principal component analysis, we don't have the groups. Okay, so we don't have that response, and we just rotate the groups to maximize the variance explained by the first few principal components. And in both cases, I'm just creating a rotation of the different axes. Okay.
Teacher, I have a question.
Sure.
In the previous slides, when you say that we have X0 and we evaluated C in X0, that we need to see if the result is more likely than C1 or C2.
Yeah, the idea of this function is, once you define the function, you can compute Z bar 1 and Z bar 2, okay? And you will assign a new observation, and I'm calling it Z0. If Z0 falls here, I will assign it to population 1 because it's closest to Z1 than Z2. If an observation falls here, if a new observation falls here, I toss a coin. It doesn't matter which group I assign it. Okay, but observations that fall, for example, if an observation is here, that's more likely to come from group number 1, right? And if an observation falls here, that's more likely to come from group number 2. So I would assign it to group number 2. So my cutoff point is the middle, the halfway between the two transformed means.
Okay.
Okay.
Thank you, teacher.
Oh, you're welcome. Okay. So what I mentioned earlier, in the case of two groups, the linear classification rule employs the same discriminant function that we saw earlier. So the Fisher discriminant, the linear discriminant function is the same as the linear discriminant function that we saw earlier. Okay. Now, I also mentioned that Fisher's approach is essentially non-parametric, but because it doesn't assume normality, but it does assume equal variance covariance matrices. That is an assumption. If we know the prior probabilities of populations, then we can use them, and the classification rule is adjusted according to those prior probabilities. Okay, we seldom know that, and so we use the algorithms that we use to compute the Fisher linear discriminant analysis or the linear discriminant analysis function. Take the sample estimates of the prior probabilities, because we seldom know those prior probabilities. The other thing that's important is if we know the cost of misclassification, we can take that into account for the decision rule. Okay, so if it's more costly to classify something as cancer than to make a mistake. For example, I have here cancer and no cancer, no? And this is what I call the actual. No, that's what Bayesians know the true state of nature. This is what the Bayesians know, true state of nature. And here I have my prediction. So my misclassification errors occur when I predict cancer and no cancer. If I predict cancer and it's not cancer, I get classification errors. And if I classify as cancer and it's not cancer, I also get my classification errors, right? We had called this thing an N11, N12, and this is N21. Now, if I have different costs, I can incorporate that information into the linear discriminant function. Okay. We can either do that, or we can also use other criteria like maximize sensitivity and so on. Okay. We'll do several examples where we'll be focusing more in other methods. Linear discriminant analysis is a very limited method because of restrictions on the variables, the predictors that we're assuming continuous predictors, and also on the variance covariance matrix assumption. Now let's look at the discriminant analysis of Fisher's data. This data is a lot of people use this data. It's been used for many years now to exemplify the use of linear discriminant analysis. Fisher introduced this Fisher linear, what's now known as the Fisher linear discriminant function. He introduced it in 1936. And the way he introduced this Fisher discriminant analysis was using an example from a data set from Edgar Anderson. It's a data set that has 3 different types of iris flowers and these 3 different species of iris flowers. A lot of people know this data as the Fisher's iris data, but it is also known as Anderson's data, because actually Anderson was the first one who published it, and Fisher used it to illustrate the Fisher linear discriminant analysis method. Okay. We have 50 samples of each one of the 3 species. And the species are Setosa, Virginica, and versicolor. Those are the 3 species of flowers. And the characteristics that were measured for each observation is one of the flowers. Okay, they measure the sepal length, sepal width, petal length, and petal width. So we have 4 measurements. The 4 are continuous. This is how the data looks like This is a chart that shows, we've seen this type of chart before. I have the marginal densities here, okay, for sepal length. This is the distribution, the one in red or sort of coral, it's coral or something like that. This one corresponds to setosa. This green one corresponds to versicolor, and the blue one corresponds to virginica. So these are the marginal distributions for this measurement, the sepal length. These are the marginal distributions for sepal width. These are the marginal distributions for petal length. And these are the marginal distributions for petal width, okay? Now, what you see down the diagonal are the scatter plots of each variable versus each other variable. For example, this is sepal length versus sepal width, okay, for the three different species, sepal length versus sepal width. So you can see here, these are the setosa. These are setosa. There's the other two are sort of mixed here, okay, but there tends to be some trend. The larger the sepal width, the larger the sepal length. And we also see that behavior here. The larger the sepal width, the larger the sepal length. However, here there doesn't seem to be that linear relationship, at least for setosa, between the sepal length and this is petal length. Okay, so we can see the scatter plots of each of the graphs, and we also have the correlations of each pair of variables. Okay, we have the correlations. There are some things that are very jump right away with this graphical analysis. One of the things that jump right away from this analysis is that we can, if we use petal width, no, this is petal length, sorry. If we use petal length, I can definitely distinguish between setosa and the other two categories, right? And the other two species. Setosa, just looking at the marginal distributions, I can see that setosa, I can distinguish setosa just by the values of setosa because their distribution is much different than the virginica and the versicolor. And it looks like if I wanted to discriminate among the three and use only one variable to predict which class a flower belongs to, I could use probably petal width. If you look at here, petal width, you'll see a separation here and separation here. So that seems to be a good variable to separate these variables. And if you look at the graph look at this graph here, the one I'm putting with an asterisk. This is petal length versus petal width. And you can see right away that if I look at those two variables, I can get a very good separation between the species. So it looks like the combination of those two variables will be the one that can give me a better separation between the three species. Okay. We'll go over this and do this exercise in a few more minutes. I just want to review here some of the commands we'll be using. LDA is the function that we use to do a linear discriminant analysis. And the function specifies which is the response. The response is the species. And I want to model that response as a function of the data in the iris data set, which has the 4 dimensions, okay? Sepal width, sepal length, petal length, and petal width, okay? Now, I have 3 classes, okay? I have 3 classes, and therefore, I have two linear discriminant functions. I have 3 classes, so I only need 2 functions to separate the 3, okay? If I had 4 classes, sorry, I have LD1, LD2, we have 3 classes, yeah. We have 3 classes, setosa, virginica, and versicolor. If we have 4 classes, we had a fourth class of iris flower, we would need 3 discriminant functions to separate the 4 classes. Okay, so these are my 2 discriminant functions. We'll review this thing when we go over the R script. Okay, these are the prior probabilities that we used as default. We don't know the prior, so the model estimates the priors as 1/3 because we have 50 observations of each. Then we have the means for each of the classes for the different measurements for sepal length, sepal width, petal length, petal width. That's the mean for setosa, versicolor, and virginica. And we have the coefficients for the discriminant functions. These are the vector A that we saw in a few slides before. These are the coefficients that multiply the original variables to classify an observation as setosa, virginica, or versicolor. Okay. This number here, this figure here, is the standard deviation between groups divided by the standard deviation within groups. Okay. So as you can see with the first discriminant function, I get a 48.64 there. Whereas with the second discriminant function, I get 4.59. And these are the proportions of variance between groups that is explained by each of the discriminant functions. So it's a proportion of variance between groups that is explained by each discriminant function. So what that's 0.99 is the percentage of variance between the 2 groups that is explained by the first discriminant function. So the first discriminant function is the one that's having the most important weight here in separating the groups, in separating the 3 classes. Whereas the second discriminant function only explains 0.8% of the variance between the different groups. Okay, and remember, the objective of the discriminant function is to maximize the separation, between groups and minimize the separation within group, the variance within each group. Okay, this is the first discriminant function and the second discriminant function. Both of these functions are linear combinations of the 4 variables. Okay, both are linear combinations of the 4 variables. We can see a clear separation here. We can imagine a straight line because it's a linear discriminant. So we can imagine here a straight line. It doesn't matter where we put this one. That's a straight line separates those 2. And then I have another straight line separating these 2. Okay. That'll be how these linear discriminant functions would map into these linear discriminant 1 versus linear discriminant 2. Now let me go back to these coefficients here. See what's happening with the coefficients. Remember when we looked at the graph and we saw, let me go back here very quickly. We saw, for example, that we get a nice separation here using the petal length and petal width. Okay. And look at the coefficients of petal length and petal width. They are much larger coefficients than the ones for sepal length and sepal width. These are twice, almost, this is more than twice than the coefficient for sepal length and so on. So there's more weight to these 2 variables because those 2 variables alone are giving me pretty good separation between the two groups. Okay. Now there's a similarity with PCA. When we looked at principal component analysis, this is how the PCA plot looked for component number 1 and component number 2, distinguishing by setosa, versicolor, and virginica. As you can see, I achieve better separation with my linear discriminant function, because the objective is variable reduction, and the objective here is classification. Okay, so in the right, I do not consider the target. In the left graph, I am considering the target. Okay. Now this set is very easy to separate. We'll look at other sets of data that are not that easy to separate. This is the histogram and the density function estimation of each of the groups based on the group 1, group 2, and group 3, and these are the transformed values. Okay, so as you can see, I get a shift of the distributions there. This chart here, I don't like it very much. This gives you a projection of the hyperplanes that separate the 3 groups, but it's projecting over each pair of variables. What you see in red are the ones that were misclassified if we only took those boundaries here. Okay, I don't think that is a useful view of a useful graph to explain how this thing works, but it's a graph that's available if you want to see how the linear borders can look like. That's how the linear borders look like in each pair of axes. Because remember, we have 4 dimensions, so visualizing the hyperplanes in 4 dimensions, that would be a lot harder. So if we look at projections into each pair of dimensions, then what we see are the straight lines that separate each group, each of the 3 groups. Okay, is it clear what these graphs look like? What these graphs show? Okay. And this is our confusion matrix. Sorry.
I didn't understand quite well what did this graph show.
See what we are working in 4 dimensions. Okay, so the 3 groups are separated by hyperplanes in 4 dimensions. So what these graphs are doing are showing, I'm going to project everything on the sepal length versus sepal width dimension. And then my hyperplane is going to look like straight lines when I project it into 2 dimensions. Okay. And those are the projections of the 3 hyperplanes, of the 2 hyperplanes in the 2 dimensions. So I have my boundaries here. This is the virginica, and this is the versicolor, and this is the setosa. And that's what it's doing. It's projecting into 2 dimensions a 4-dimensional hyperplane.
Okay, thank you.
This is the confusion matrix. Now, this confusion matrix is computed based on the same sample that was used to train the model. So there's no surprise that it gives very good results. The accuracy is 1, that is 100% correct classification. It's a confidence interval for the accuracy. And we have, in this case, we have sensitivity with more than 2 classes. Sensitivity can also be computed, but when we have more than 2 classes, we normally look at just the confusion matrix is in the percentage correct classification. Okay. 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 Before we take the break, this linear discriminant function works fine if I can separate my groups with a linear function. There will be many cases where I cannot do that. I cannot separate my groups with a linear function. Okay. Now, there's other methods that we'll be looking at to be able to deal with situations like this, where I have a non-linear separation of the groups. Okay. And we'll be using neural networks. We'll using support vector machine. Okay. Those are the main two nonlinear methods that we're going to be looking at for classification when we do not have linear boundaries. Now, of course, the more separated the groups, the populations are, the better. This is, for example, a case. In this case, we have two groups that have normal distributions, but different means and variance, different covariance matrix. You can see the variance here. In this case, it's just the variance. It's just one-dimensional variable here. P is 1. So we can see that we have more variability in this population than the other population. So we'll look at this case when we talk about the quadratic discriminant analysis function. Okay, because here we have different variances. Now, the other thing that we should keep in mind, that confusion matrix that we just saw was computed based on the same sample that was used to train the linear discriminant function. Okay. What we will be doing in the class, will always be doing, and because it's good practice, it's very important to separate our data into a training data set and a validation set. Okay, training and validation. Now, what percentage of data should we devote to training and what to validation will depend on a lot of factors. We definitely want to have a large enough training data set, okay, but also a large enough validation data set so that we can encounter situations that may not be in the training data set. So a good criteria here, and depends on sample sizes and the number of predictors that we have. But ideally, we should be using between 75 to 80% training and between 20 and 25% for testing or validation. I'm going to call it validation. Okay, then we'll later talk about procedures, how we deal with this training data, because there are things we can do with that training data to ensure that the estimate is robust. Okay, now sometimes we cannot do this thing because we have very small data set, but if we have enough data, we can definitely, there are cases, for example, where in that project that I told you with money laundering, we had millions of transactions in a year, so we were able to use 85% for training and 15% for validation. Okay, so that it depends on how many predictors and how large your data, your sample is. Okay, but it's always good practice to evaluate a model with data that was not used to estimate the model or to train the model. Okay.
Teacher, from where we are taking the iris variable?
The iris data set is just call it, it's just named iris, and it has this column: sepal length, sepal width, petal length, petal width.
Okay, but it is
it comes with R.
Okay, perfect.
Yeah,
Thank you, teacher.
It comes with R. Are you all set?
Yes, teacher, down to the line with the plot.
Okay. Okay, so that's a plot we already saw in the notes. Okay, we explained that what that plot is telling us. Now, to do a linear discriminant analysis, we use the library mass, the package mass, and the function is LDA, linear discriminant analysis. And since the IRIS dataset contains all the variables, and I want to do a discriminant analysis using all the variables, I can just specify species, which is if you look at the names IRIS, that's sepal length, sepal width, and the response is species, okay? So LDA takes the species as a response as a function of all the other variables in this data frame in IRIS. Or you can specify each of the variables. Suppose you wanted to do a discriminant analysis, not use all the variables, we could do it this way, okay? So I'm going to do this LDA fit, and the response I get is what I showed you in the notes. You have the prior probabilities. You have the group means for each of the 3 species. And we have the coefficients of the linear discriminants. Okay. So how does this work? If suppose a new observation, a new flower comes in with certain sepal length, sepal width, and so on. So we would multiply the sepal for the new flower. We would multiply the sepal length times 0.82 plus 1.53 times sepal width, and so on. And we would do the same for the second linear discriminant function. And we will assign it to the population where that value is the largest. Okay, to either setosa or iris or whatever. Okay. Now, it shows here the proportion of trace. The proportion of trace is the proportion explained by each linear discriminant function of the total of the variance between the 2 groups, between the three groups. Okay, so the first one explains 99%. The second one explains 88%. Now, let's look at what LDA fit has. I put the model in LDA fit. LDA fit has all those components, has the prior probabilities, has the counts, which is the number of observations in each class, has the means, has the scaling, which are the coefficients for each discriminant function, and has the LDA fit SVD, which is the standard deviation between groups divided by the standard deviation within each group. Okay. Now, we already saw that this is the proportion of trace, and that essentially, if you look at that, scaling is just the coefficients, okay? SVD is the proportion, the SVD is the coefficient between the ratio between the standard deviation between groups divided by the standard deviation within each group. Okay, that's the SVD. So if we square that, that will be the variance between groups. This will be the variance between groups and the variance divided by the variance within groups for each of the linear discriminant functions. And what we saw earlier as the trace, which is listed here as the proportion of trace, is essentially the proportion of variance that is explained by each of the principal by each of the discriminant functions. If you look at that, if I take the variance between groups, okay, divided by the sum of the variances within each the sum of the variances of each that explains each of the discriminant functions, that's a proportion that is explained by the first discriminant function. Okay, so that's the prop and the second one. So it gives me the same number here. It's a 0.99 and 0.008, which is what we have here. These are the same as the trace, the proportion of trace of the variance covariance matrix. Now let's do a prediction. Again, this is not what we should be doing. We're going to predict the same data that we used to feed the model. So I'm going to say to predict, we use the function predict that works with linear discriminant functions, that works with support vector machines, that works with any of the algorithms that we will be using. So I'm going to create a data frame called pred.lda, which will have a prediction using the model that I just fit and using the new data, assuming that the new data is the same data that I have. So I take the same data I have and use it as new data to make the prediction. Okay. If I look at what pred.lda has, pred gives me the class, the posterior probability, and X. Let's look at the class gives me whether it's Setosa, Virginica, and so on. The posterior gives me for each of the different species, it tells me what are the posterior probabilities for each of the classes. For example, this one gives me a very small posterior probability here for Setosa and very small posterior probability here. So let me show you. Let me do something here. That's the head of. I'm going to list pred LDA. The data are ordered, so I'm going to use posterior, but I'm going to list the rows 1 through 10, and then I'm going to do pred. Dot LDA posterior 1 through the 51 through 60, and pred. Let me see, structure of pred LDA. I just want the posteriors. I want the, okay, I'll do this thing. Pred LDA. I wanted to list the middle one. Okay, I'll do tail. Let me do tail. Tail of pred LDA posterior. Okay. That's a posterior for the distribution for the tail. Okay, if you look at the head, Setosa is the posterior probability is 1. Okay, so this observation is being classified as Setosa, which in fact was actually Setosa. Okay, remember, these are the posterior probabilities. This is a probability of close to 1. It's not exactly 1, but it's very close to 1. And these are very small probabilities. Whereas if I look at the tail, I have very large probabilities for Virginica. So these last records, these last observations are being classified as Virginica because that's the highest probability. Okay, so these posterior probabilities tell me the highest probability indicates to which class that observation is being assigned to or predicted to belong to. Okay, and then I did a cbind here to have the predicted class, the predicted posterior, and the actual class, and the X value for that observation. So you have, say, notice first I'm doing this is actually class 1. The first one, the first column tells me what's the actual class. Then what's the predicted class? what's the posterior probability for that class, for that observation, and the predicted probability for versicolor, predicted probability for Virginica, the linear discriminant function 1 and the linear discriminant function 2. Okay, the coordinates that I get after I transform using the linear combination for each of the variables. Okay. Now I'm going to use another library here, scales, to graph the discriminant functions, and I'm going to do the new data. I'm going to take type data equal iris, the fifth column. Okay, that's the type. So I'm going to use the type as the fifth column. Remember, the fifth column is the class, and the predicted corresponding X. That's I'm going to call the new data. Okay, so I have the new data, and to generate the plot that we saw earlier, where I'm graphing the data versus the first discriminant function and the second discriminant function. I'm taking the first discriminant function, and y is the second discriminant function. Okay, to see how this the scatter plot looks like for the first and the second discriminant function. The density functions and histograms that we saw are obtained with this. I'll do a plot LDA fit. Remember, LDA fit is a model. Okay, if I plot the LDA fit, plot will recognize that LDA fit is the result of a linear discriminant function analysis, and will plot accordingly. I can change the colors here, but I leave the same colors. So I'm plotting the first discriminant function, the data for Virginica, Setosa, and versicolor, the marginal distributions versus the first dimension, the first linear discriminant. Okay, the Z1, the transform Z1. And the other chart, which I don't really like, but I want to show you can do it, is with this package CLAR, and that gives you these charts. Okay, which I honestly don't find very useful, but if you want to use them, that's fine. Okay, and you select the colors you want. I chose some colors here. That's it. And to compute the confusion matrix, we're going to use Caret, a library that we'll be using very often, and the function is confusion matrix. And for the confusion matrix, we tell Caret, what are my classes, my predicted classes, and what is the reference. Okay, so this is the prediction, and these are the estimated or the these are these are the references. Okay, these are from the original file, from the iris file, what are the actual species, and these are the predictions for the species using the model. That's the confusion matrix. Okay, and that's here it gave me an accuracy of 0.98, which is different from what we got in the presentation, but still very high. Now, what we mentioned earlier is that we will always be separating our sample in a training sample and a validation sample. Okay, we're going to be using this function from Caret, create data partition. Create data partition has the advantage of if, for example, if I'm predicting fraud and only 1% of the transactions in my whole data set are fraudulent transactions, with create data partition, I make sure that the training data set contains only 1% of fraud transactions and 99% of non-fraud. And my validation data set has the same proportion. So I keep the proportions from the total sample. In this case, it doesn't matter because I have 50, 50, 50. I could just use random sampling and it would be exactly the same, okay? But we'll be using this in general to ensure that we keep the proportions equal in the training and validation sets as we have in the original data set, okay? Now, how's this function used? And we'll be using this function very often. I'm gonna create a data frame with the rows that I'm going to use for training. So in this case, I'm going to use 80% of the data for training. Now, I have to specify which is my class variable that will be used to ensure that the proportions in training and validation are the same. So I use the function create data partition. Then I tell the function which is the class variable that I'm going to be predicting, and the percentage present of each of the classes in the whole data set is the same proportion that's going to be preserved in the training data set and the test and the validation data set. So I'm going to use 80% of the data, and I'm going to create this data frame that has the rows that will be used for training. The least argument equal false is important so that I get the training rows as a vector of rows. Okay, you need to use least equal false. Otherwise, it'll give you a data frame, and then you have to manipulate that data frame to get the rows. So least equal false. This thing, I said the seed here just because the way this thing is, this is creating a random partition. So it depends on the seed that it will use to generate the partition. So, and if I want my results in my computer to be reproducible, I set the seed before. Okay, even if you use the same seed, you will probably get different values, different observations, because the random generator depends on the computer, the speed clock, and so on. So I set the speed training rows. So if you look at training rows, all it does have is the number of rows. Okay, number of rows that are going to be set up aside for training. Okay, so how do I do that? I create a new data frame, which I'm going to call iris.train, and that will have all the rows that correspond to the training rows in this frame. See, if you look at training rows, look at my environment here. Training rows has 120 rows, okay? Because I'm devoting 80% of my 850 observations for training, okay? So I'm gonna use, in train, I have now at 180 rows formed by the rows specified in training rows. In test, I'm gonna have iris minus all the rows that are not part of training rows. Okay, and that's iris test. So in test, I have 30 observations, look here. And in training rows, I have 120 observations. That's my total of 150. If I check the proportions in training and in the whole set, I look at I use the function prop.table to get the proportion table of the table of the classes of species. Okay, so in my original set, I have 33% of each, and in the training set, I have 33% of each. So the percentages are maintained with the create data partition. Now I'm simply going to repeat the exercise, and I'll use the same library mass. Now I'm going to call it LDA feed 1, and I'm going to use only the training data set here. I have LDA feed 1, I have the coefficients and so on. As you can see, the results are very similar, 99% and 0.8%. And I'm going to classify the test data using the model that I just got. So I'm going to say pred.lda, and I'm going to predict using the model that I just fitted now, okay, which is LDA fit 1. In the new data, I'm going to use iris.test. I'm going to use the test data, which were not used in training. We know that pre-test the LDA has. We already saw the structure, and that's the posterior probabilities. And these are the X1 and X2 for the linear discriminant coordinates. I'm gonna combine the class, the posterior, and X to look at how the classification was done. And I'm going to do a data frame, okay, which with the species equals iris.test, and I'm calling it species. Okay, that's using the column species, and these are the linear functions, the linear discriminant functions. Okay, that pred, and now I'm going to use the confusion matrix, and that's the confusion matrix. It changed. It's essentially the same thing, 95%. Okay. Now, what I want you to do, I want you to take the data that we've been dealing with, the Swiss bank notes data, and do a similar analysis. Okay. Now, forget about doing the analysis with all the data set. From the beginning, split your data set, creating data partition, split your data set in, let's say, use 80% of the fraudulent nodes on the, I'm sorry, 80% of the total data set, the Swiss bank nodes, for training, and 20% for validation. Okay. 80 and 20% for validation. Remember, use create data partition, although we know that in that data set we have 50% of the good nodes and the bad nodes. Okay, so I'll split you in teams. Any questions so far about what needs to be done?
I don't think so.
Okay. So I'll give you, see, it took us about 15, 20 minutes to do this thing. I'll give you the same 20 minutes, okay? Well, I'll check with each room. If you have any questions, just let me know, and I'll enter your room to answer.